we're officially live. I'll be right back. Can you hear me? Nice. Okay. I'll let people log on for another minute, and we'll get going. I sound like Wally. Is that true?
I don't know what
I don't remember what Wally sounds like.
Does someone say that?
Is that a knock on the audio quality, Alex? I don't know what you mean by that. Shit. Sweet. In 8th grade, my math teacher called me Eeyore.
Why?
because I sound like Eeyore.
I see that Eeyore doesn't even talk, does he?
Yeah, I think so. And I think he's just like, okay. So, excuse me. I will say I have not seen the final. I don't know what it looks like. I don't know if Jeff is making it harder. I would guess not. I would expect probably something comparable to the midterms. But to be honest, I don't know. I haven't seen it myself. So, all right.
Are you going to see it?
I don't know. In the past, he's sent the exams to us, but not this time yet. All right. Well, hello, internet. Hopefully, you guys are doing well. I'll get started. My plan for the review session is going to be the same as usual. The only difference being that it's going to be very quiet in this room, and you all will be watching online. I have a bunch of examples prepared. Like I said, if at any point you either can't hear me or can't read something I write or don't understand anything, I've got my eye on the chat. Oh, Jeff hasn't made the final yet. All right. I've got my eye on the chat so you can ask questions there. Otherwise, we'll get started. I want to warm up with something easy first. Yo, let's compute an arc length. That'll get our blood flowing, and then we'll move on to some real stuff. Okay, so the first, also I need to make sure. Yeah, I'm using a wired mic, so. At my 31B review session a couple nights ago, we almost had a disaster. Okay, one thing that we definitely all need to be able to do is compute arc length. So the kind of example that we'll start with is, here's a curve, and I want to compute the arc length of the parametric curve given by t cubed minus 1 and t squared plus 3 from t equals 0 to 1. Let's do that. Okay. So what do we do? The thing to remember is the arc length formula. So recall that the arc length that we care about in general is the integral from a to b, where a and b here represent the time parameters. So in our case, a is going to be 0, b is going to be 1. And then the thing that we integrate is the magnitude of the speed. Speed is just the norm of r prime. Also, like I said, for you guys, if you can't see, you can feel free to move wherever you want. Cool. Okay, so an arc length problem like this is just a matter of setting up an integral and doing the integration. So for us, let's see. The arc length that we care about is going to be the integral from 0 to 1 of the norm of r prime of t In this case is going to be the vector 3t squared, 2t. Then we have to remember how to take the norm of a vector. It's the squared sum of the components under a square root. So this will be the square root of this quantity squared is 9t to the fourth. Here it'll be 4t squared. Now we have to figure out how to do this integral. Now, I talked about this, I think, in the past when we did arc length problems, but one thing to keep in mind, for tomorrow at least, is that strictly speaking, 31b is not a prerequisite for 32a, so the kind of integrals that you'll get are not going to be crazy. No trig sub, no partial fractions, nothing like that. Strictly speaking, the only integration techniques that we have in 32a are algebra and substitutions. So anything you get in an arc length integral should be able, you should be able to use only those things. And indeed, if I look at this, what I'm tempted to do is I see a common factor of t squared in both. I can factor that all the way out, pull it through the square root, and see if that helps me at all. So that's what I'll do. Factor out a t squared, and then pull the t squared through the square root to get a t. That leaves us with a 9t squared here, and then a 4. Okay, and then I think that's helpful because after this, I have a pretty obvious composition of functions and then a t sitting outside here that I can pair with the differential. So what I'm tempted to do is call this thing u and do a substitution. So I'll let u be 9t squared plus 4, probably. Then du is going to be 18t dt. And every time you do a substitution, whether you like it or not, you've got to change the bounds. So when t is 0, what is u? U is going to be 4. And when t is 1, u is going to be 9 plus 4, which is 13. Okay. Uh-oh. I latched myself to my computer and I didn't grab the eraser. Shai, do you want to get that for me? Thanks. All right. Du has a factor of 18 in it, so t dt will be 1/18 du, and then we'll be left with the square root of u du. Now it's a power rule problem, and we're in the clear. So power rule says this is u to the 1/2, increase the power by 1 to 3/2, divide by 3/2, evaluate at the upper and lower bounds, and that'll do it. So we've got 13 to the 3/2 over 3/2 minus 4 to the 3/2. If you want to, you can simplify. I've got better things to do, so I will not. And if that means I lose a point on my test, so be it. Okay. I'm all warmed up now. Hopefully you guys are. Hopefully the lag isn't too bad. I don't know what I can do about that. But that's an arc length problem. moving on. Oh, anytime I draw a square, that means I'm done with my solution. That's the Joe math grammar. Nice. All right, let's do this. Also, yep, means QED, kind of. All right, here's the next example. It's going to be a multi-parter. I'm going to give us a function. Let f of x be f of xy be 2x squared minus y squared. In part A, I want to compute the linearization at some point. So compute the linearization, which I'll call L of xy, at the point 1, 1. In part B, I want to use this to estimate f of 1.2, 1.1, I think. Okay. This is pretty standard for what we've done so far through the quarter, and then I'm going to throw a curveball at you, which I think maybe is a little tricky, maybe not. I don't know if I would necessarily expect something like this, but if you want kind of something to make sure that you really, really understand what's going on, the question is, in part B, is your estimate an underestimate or an overestimate? So is your estimate an under or overestimate? Okay. That's next. Yeah, so the previous problem we just did, that was purely just computing arc length, not an arc length parameterization. Maybe later tonight or sometime tomorrow, we can do an arc length parameterization problem, which is a little more involved, but the main computation is still computing arc length. Sweet. All right, so let's do part A and part B. These will be relatively routine, and then we can think about part C. So part A, compute a linearization. The thing to remember is the linearization formula. And this is the thing that mimics the tangent line equation in one variable. Or if you like to think about it this way, it mimics the first Taylor polynomial formula. So recall that the linearization at the point AB, the formula for this is f of AB plus the x derivative at AB times x minus a plus the y derivative at AB times y minus b. You know, something to just remember, or since it's an open book test, you don't have to remember it. But like I said, this is a direct extension of just how to compute a tangent line, only in in higher dimensions. In words, all this thing is saying is that if you want to approximate the behavior of f, start at the point, and then if you move a little bit in the x direction, how should you change? Approximately by the x derivative. Likewise, if you move a little bit in the y direction, how should you change? Approximately by the y derivative. That's what this kind of thing is saying. So to compute a linearization, it's just a matter of spitting up this formula, and then we'll be done. All right, so we'll need f of AB, we'll need fx of AB, we'll need fy of AB. So first, f of 1, 1, which is our AB, it looks like is 2 minus 1, which is 1. The x partial as a function is, if I take the x derivative here, I'll just get 4x. So this tells me that the x partial at AB, at 1, 1, is just going to be 4 times 1, which is 4. Do the same thing with the y derivative. The y derivative as a function is negative 2y. So the y derivative at the point that we're evaluating at is just going to be negative 2 times 1, which is negative 2. In that case, so what I'd actually say is that the problem shouldn't say something like that. Like when you compute a linearization, you're computing at a point in the domain. They could say something like compute a tangent line at the point 1, 1, f of 1, 1 or whatever. But hey, Mark, how'd the test go yesterday? Anyway, I don't think that they would ask a question exactly like that. When you compute a linearization, it's strictly based at a point in the domain. Okay, well, let me write down the linearization, and then I'll make a comment because I was the one that graded the linearization question on the midterm, and I just wanted to point out maybe a sort of common mistake that I saw. Anyway, if I vomit up this formula, that tells us that the linearization at the point xy is f of AB, that was 1, plus the x derivative is 4 times x minus 1. And then the y derivative was negative 2, so this will be negative 2 times y minus 1. Okay. That's the linearization formula. Really quickly, just because I've got all the time in the world, some common errors from midterm 1 or midterm 2 when you had to do this kind of thing. One of them was to write like delta x here or something like that. Like I saw a lot of things that looked like L of xy is 1 plus 4 delta x minus 2 delta y. That does make sense. I know what you mean by that, but the linearization is a function of x and y. It needs to be an equation where you plug in an x value and plug in a y value, and writing something like this, it doesn't make sense. So that's no good. Another maybe less common thing that I saw is people, a handful of people wrote down this formula, but then like with these derivatives here, they just left the derivative as a function, as the coefficient. And again, that doesn't really make sense either. So what I mean by that is something like 1 plus 4x times x minus 1 or something like that. That also is incorrect. We specifically want those numerical coefficients. Anyway, not a big deal, just figured I'd point that out. Why do I put AB instead of 1, 1? So I don't know if you're referring to this, but I wrote A, B there just because that's the formula for any. Okay. Anyway, that's the linearization. That's part A. Part B, which I'm going to have to erase 0.2, 1.1 into this expression, and whatever that spits out, that's your estimate for the value of f there. So for part B, we could say f of 1.2 comma 1.1 is approximately equal to L of 1.2 comma 1.1. Oh, another very small thing that I saw people do is I would say the linearization is approximately equal to this. That's also incorrect. The linearization is literally equal to this. The point is that f is approximately equal to the linearization. Anyway, so plug in 1.2 and 1.1 into the linearization here, and you'll get 1 plus 4 times 1.2 minus 1 is 0.2. And then minus 2 times 1.1 minus 1 is 0.1. Then I guess we could simplify this. 1.8 minus 0.2 is probably 1.6. Nice. All right, part B. Like I said, that's relatively routine, and I think this is definitely something standard that you should for sure be able to do. The trickier part of this is, what did I ask next? I asked, is this likely to be an underestimate of the true value or an overestimate of the true value? Oh, it's right there. Is our estimate an under or overestimate? I know what I would do because I wrote the problem. But I'm curious if anyone, either in person or online, has any thoughts.
You just compare it to having
Okay, so that's a good point. So here's one way you could do that, is you could just figure out, to f of 1, 1.
Yeah.
Well, that wouldn't tell me much, because what I'm curious about is how this relates to f of 1.2, 1.1. Yeah. Yeah, so the concavity is the point. So Jordan suggests thinking about the concavity, and that's exactly the idea. I think it helps to think about this in the one variable setting. So let me erase this stuff. If I asked you this question with a one variable function, the thing that you would do is you would look at the concavity of that function at the point. So for part C, in the one variable case, if we had a function and I went to some point A and I computed the linearization at that point, I would get something like this. And then if I asked, over here at some point B, how does the linearization approximation, how does this compare to the true value of the function? The way I've drawn this picture, the key is the fact that the function f is concave up. In other words, the key is that the second derivative is positive, which indicates that the linearization is going to lie below the function. If the second derivative was negative, the linearization would lie above. So in some sense, concavity is the key. The maybe slightly tricky part about this one is that we haven't really talked, we kind of have, but we haven't really talked about concavity in a multivariable setting. So we have to be a little careful about what we mean by check the concavity. you know, because you can take a second derivative, but there's 4 of them. So which one would we take? There's probably a couple ways that you could do this correctly. What I would do is I would think about looking at the concavity in the direction of the thing that we're approximating. In other words, if I, let me draw a picture of our domain. Here's the point 1, 1. Definitely not to scale, but here's the point 1.2, 1.1. Roughly what I want to do is I want to take a trace of the function where I chop like this, and then I look at the concavity of that thing. In other words, what I really want to do is I want to take like a second order directional derivative going this way. So one way to do that mathematically is I could parameterize this line segment, feed that into the function, and then take a second derivative. Roughly mimic how we take directional derivatives, but just do that with the second derivative. That's kind of tricky. Let me do that. And like I said, if you watch this and you're like, Joe, what the hell did you just do? Don't worry about it. This is a little tricky, and it's more of a conceptual thing to get you thinking. I don't think you'd have to do something like this, but let me do it anyway. So if it were me, like I said, there's probably conceivably a couple ways you could formalize this, but I would parameterize this blue line segment from 1.1 to 1.2, 1.1. So I would let R of t be, well, I'm starting at 1, 1, and then I'm traveling in the direction 0.2, 0.1. And here's a parameterization of this line segment. I could write this as 1 plus 0.2 times t, and then 1 plus 0.1 times t. And what I want to do is I want to compute the second derivative with respect to t of f of R of t. This is measuring the concavity of the function in this direction. So then it's just a matter of computing this. So this would be the second derivative of, what is f of R of t? So I erased f a long time ago. I'll remind you what it was. F was, if I can remember, 2x squared minus y squared. So f of this would be 2 times 1 plus 0.2 squared, t squared, minus this quantity squared, 1 plus 0.1 t squared. Take a second derivative of this, and that'll tell me what the concavity is in the relevant direction. So the first derivative, let's see, is going to be, by the chain rule here, 4 times 1.1 plus 0.2 t times 0.2 minus, derivative here will be 2, 1 plus 0.1 t times 0.1. Take another derivative and then we'll be done. So then the derivative of this, I'm just going to pick up a factor of 0.2 here. So this will be 4 times 0.2 times 0.2 is 0.2 squared. minus 2 times 0.1 squared. This number is definitely positive because this one is for sure bigger than this. So this is positive. That means in this direction, the function's concave up. So I expect the linearization to lie below, which means our estimate is probably an underestimate. Since f is concave up in this direction, the linearization at this point is likely to be an underestimate. Okay, done. Try.
2 questions. One,
Yeah.
is that the same thing as chain rule for paths?
Yeah, so one way to think about what I just did here is I used the chain rule for paths, which is nothing like high-tech or fancy. It's just the chain rule. Half of the things in calculus that have a special scary name are just the chain rule. But yeah, exactly what I did is I composed a function with a path, and then I just took the derivative. So we could have phrased this in terms of some like chain rule for paths type stuff. Yes.
Do we say likely because like we're assuming the concavity doesn't change?
Yeah, because the reason I say likely is because what could happen is you have something like that's concave up. Oh, but then it goes down like this. And then, you know, here's the linearization. And maybe it went down so quickly that 1.2, 1.1 is like over here. And so I was basing concavity like around here. Although actually what this shows, since the second derivative was constant, it's like always concave up. So this doesn't happen. But the second derivative, this kind of argument, strictly speaking, doesn't really tell you what's happening just because something like that could happen. But in this case, it actually does.
If the second derivative hadn't been constant, we would have done something in terms of t.
Then I would have plugged in the 0.11 to get the second derivative at this point if the second derivative wasn't constant.
But the second derivative is in terms of t. So you just find t, that one.
Which would be 0.
Oh, duh.
Yeah. Tricky. All right, that's maybe a 32A honors question, so don't worry about that one if it's confusing. All right, another one down. Let's knock out a limit. How about that? There actually is a 32A honors, but it's not offered every quarter. I think it was offered back in the fall. I'm not really sure, actually. It exists, though. All right, next up. Just to spice it up, evaluate or show that it doesn't exist the following limit. The limit as xy goes to 0, 0 of, let's do x cubed y over x to the fourth plus y to the fourth. Okay. Now, to recap my general flow chart of attack with a limit, if I don't know what to do, the first thing I always try is maybe I can just plug it in. I'll move out of the way. Sorry. That will almost never work, but it could, so you should think about it. And then if that doesn't work, usually the next thing I try is approaching along the axes. If that doesn't work, I'll try approaching along y equals x or something like that. And then if that doesn't work, I'm thinking about the squeeze theorem. Otherwise, if I see x squared plus y squared, I'm thinking polar coordinates. That's a good summary of pretty much all of our techniques for dealing with limits. So let's run through some of those. Yeah, John.
On our midterm, I think they were giving us partial credit for just trying those things. Was that
Maybe?
was that the case?
I'm not sure. But yeah, so the question is like, what if I get a limit and then I just get stuck and nothing I'm doing is working? If you show the things that you try that don't work, that could be worse than partial credit. So like if you try a handful of different approaches, but they all give you 0, which would tell you nothing, right? Like strictly speaking, you haven't shown anything. But yeah, it could be worse than partial credit. So it's never a bad idea to try things if you can't get the correct solution and just exhibit that you're doing something. Yeah. Cool. Okay, so let's run through that here. First thing I try, can I plug it in? Nope, because the denominator will be 0, the numerator will be 0. That's an indeterminate form, so I won't be able to just evaluate this like that. Okay, so then the next thing I think about, and this is usually something that I can do in my head to kind of get me on the right track, is approach along the axes. I'll write that out, but maybe I'll do it in my head. What do I mean by approaching along the axes? Mathematically, I just mean setting either y to be 0 or x to be 0. So for example, set x to be 0, and I'll write this out more formally when I do my solution, but like I said, right now I'm just kind of brainstorming. If I set x to be 0, I get 0 over y to the 4th. That's 0. So the limit here would be 0.
Can you explain again why?
Yes, I will. And I'll do that more precisely when I write this up. For now, let me just say that you get 0. Likewise, if I set y to be 0, I get 0 over x to the 4th, which is 0. So it's also 0. Audio is weird now. Uh-oh. Okay. Now, this doesn't tell me anything. The fact that both approaches are going to give 0, and like I said, I'll write this up more carefully in a sec, but the fact that they're both approaching 0 doesn't mean that the limit equals 0. It means we don't know. Yeah, so this is another thing that's come up a lot, which is, in the homework or if you read the textbook, one of the things that the book does is it's like, oh, approach along y equals mx for all lines m, and then you show that it depends on m. You don't have to ever do that. I don't think I ever do that, to be honest. To show that a limit doesn't exist, it takes 2 approaches. All you need is 2 different things that give you different numbers. That's it. That's why when I approach a limit, I'm usually never thinking about like, oh, y equals mx. I'll probably just pick y equals x or something, which is what I'm going to do here. I'll pick x equals 0 and y equals x, and that'll be it. So I would say, yeah, as long as you exhibit that there are at least 2 approaches which give you different things, however that works, you wouldn't need to do like for all m. Unless the problem, tells you. Quick thing in my head, which like I said, usually in my head, what I do first is I check the axes. And then if that doesn't work, the next thing I try is probably y equals x. I approach along a diagonal line. And I can already see that if y equals x, this is like x to the 4th. over x to the fourth plus x to the fourth. That's like 2x to the fourth. So this will be like 1/2. And that is different than 0. And that's what will allow me to show that the limit doesn't exist. And that would do it. Okay, this was just game planning. Let me actually write up my solution as I would on the test, and I'll talk about this indeterminate form issue. Okay, but so I latch on to the fact that on the one hand I can get 0, and then on the other hand I can get 1/2. Those are different, and that's what will show that the limit doesn't exist. So let me start out by doing this. So first I'll approach along the y-axis, for example, which is given by the equation x equals 0. Mathematically, how do I do that? I just take the limit and I assume that x equals 0. Whoops. It was a little awkward. Now, if I set x to be 0, in the numerator, I'll get 0 cubed times y over 0 to the fourth plus y to the fourth. And then the one thing that gets tricky about this kind of stuff, and this was the question that came up, is like, how is this still not an indeterminate form? Here's the way to do this. First of all, this expression here, to send a point like this to 0, 0, it suffices to just send y to 0. So this turns into a single variable limit as y goes to 0. The numerator is 0. The denominator is y to the fourth. Okay. Now, so the question then was like, oh, I plug in 0 and it's indeterminate. It's 0 over 0. What's the deal? No, because, so ignore the limit sign here for the moment. If I just walked up to you and I gave you this number on the street, and I said, what is that? What would you say? It's 0. Specifically because y is never 0. Y is never 0, so this number that I just handed to you is straight up 0, which means that the limit we're computing is actually just the limit of 0, which is 0. There's no indeterminate forms here because you never get to something like 0 over 0 because this expression was 0 from the start. It's very subtle and it can get confusing, but I wouldn't think about it too hard. It's just relying on the fact that this fraction here is 0. An indeterminate form of 0 over 0 is when you have both things approaching but not equal to 0. Yeah, it's a big problem. People trying to give you math on the street.
I have a question.
Yes.
Are you allowed to? So we were able to approach along the x-axis or the y-axis.
Yes.
Wherever we were able to set x to 0, because like y, because you're not setting the denominator to 0 by doing that.
Correct.
You still have a y fourth. So what if setting x and y to 0 would make the denominator identically 0?
Then I would say that the function actually wasn't defined on that axis.
So you're not allowed to approach it.
Correct.
So you're
Yeah.
supposed to do this.
Correct. Yep. Yeah, so the question is, when we do either this or what I'm about to do next, like when I approach along y equals x, I turn things into a single variable limit. Can I use something like L'Hopital then? Yes. So the tricky thing about L'Hopital's rule is that there's no multivariable L'Hopital's rule. But once you pick a path approach, that corresponds to constructing a one variable limit. And then you have any technique from one variable calculus at your disposal. That's correct. All right, so next, I've got 0. I want to do this next. So I'll approach along y equals x. Like over there, this just amounts to restricting all the y values to look like x. I want to send this point to 0, 0. And when I do that, I'll get x cubed times x over x to the 4th plus x to the 4th. Then, like I said over there, to send a point xx to 0, 0, this just, it suffices to send x to 0. So this turns into a single variable limit. This is x to the 4th over 2x to the 4th. The x to the 4ths cancel out, and you get 1/2, as I suspected here. 1/2 is not 0, so therefore, the limit doesn't exist.
Is the only way to like show that it actually exists is like using polar or?
Very strictly speaking, the only way to actually show that a limit exists is the squeeze theorem. Even if you do polar coordinates, technically you have to use the squeeze theorem, but for 32A purposes, I would think about the squeeze theorem and polar coordinates as the only ways to actually evaluate a limit, or continuity, I guess, if plugging it in just works. So since 1/2 isn't 0, the limit does not exist. Nice. Okay.
Polar, you can't show that it exists?
Yeah. Yeah. So we could approach along y equals mx here. The only thing you have to be careful about is that if you approach along y equals mx and you get 0 for all of them, for example, that still doesn't mean that the limit is 0. Because only approaching by linear paths, is not quite sufficient. So you could do that, but yeah. Then the other question is, how do we know that we can approach along y equals x? What about y equals x squared? You can try if you want, but yeah, you don't have to do this. There's probably a whole lot of other things that you could do. I just usually think about y equals x as my next option because it works a lot. That's why I did that. I don't really have a deeper reason beyond that. So if you approach along y equals mx, you would have accounted for all lines. So if you're asking like, oh, could I have done this from the start? Like, yeah, sure. You can do whatever you want. Yeah. So you're correct. The only thing you have to be careful about is if you do y equals mx and it's like always 0 for all lines, that doesn't tell you anything. Do they have to be equal to 0 when you approach? So whatever approach you take has to go through the point. I don't know if that answers your question, but like in this case, x and y are going to 0, 0. So any path I approach along the point -1, 1, I could not use y equals x because y equals x doesn't go through that point. So on the midterm, if you approached from all lines, we were only given partial credit. I think it depends on what else was going on in your solution. Because approaching from all lines, well, are you talking about for the sine one? That's the only one from the midterm I remember, the one that had a sine in it. The idea from the midterm ones was, at least for the sine one, is that you can exhibit two different paths that give you different values. That's it. So like in the midterm problem that had the sine, I would do one of the axes and then y equals x. I think if you check out the solution I wrote, that's what I did. So I think it depends on what else you did in the solution. I could always look at it in particular. All right, let's move on. Oh, let's do one of these tangent plane parallel thingy type problems. Okay, so find the points on the surface given by the equation. What did I cook up? X squared plus xz plus yz equals 14, where the tangent plane to this is parallel to some other plane that I'll give you. Is parallel to 4x plus 2y plus 3z equals 0. Okay. So same kind of thing that we had for homework, same kind of thing that was on the second midterm. I've got some surface sitting in space, and then I've fixed some other plane over here, and I'm trying to find where on that surface the tangent. Excuse me. Is anyone eating anything good right now? I'm just curious. You can let me know. What's the point of a question like this? The point is that to determine when two planes are parallel, we check their normal vectors. So the relevant fact for these problems is that two planes are parallel exactly when their normal vectors are parallel. So let me write that down. Planes parallel. This is the same thing as saying their normal vectors are parallel. Nice. Shake Shack sounds good. Trying to be a good YouTuber and interact with my audience. Okay. For the plane, when we stay. No, I don't think. So what I would do is I would just write down, and what I'll do next is I'll just say the normal vector here is 4, 2, 3. And I don't think you have to give any other justification beyond that. So the normal vector for this plane is like opposite to the tangent plane of this thing look like. Vitamins, nice. It's healthy. Yeah, I guess so. I have regular gummies. I don't have gummy vitamins. You want to pass me a? Right?
Sorry, that was
it's all good. All right. Okay, so how do we compute the normal vector to tangent planes of this thing? The point here is that we can realize this surface as the level surface of a 3-variable function. So I would say let f of x, y, z be all the variables here, this stuff, x squared plus xz plus yz. The point being that this surface that we care about is a level set of this thing. It's a level surface. Then the surface is the level surface f equals 14. The point there is that we know that we know that the gradient is always perpendicular to level things. So to get a vector perpendicular to this surface, which is what we want, we can take the gradient here. So since the gradient of f is perpendicular to level sets, a normal vector to the tangent plane at any point at x, y, z, the gradient of f, which in our case is going to be the vector, the x derivative it looks like is 2x plus z. The y derivative is z. And the z derivative is x plus y. Okay. Okay.
Once you're like into a certain number of variables, what does it mean for the tangent vector to be, for the gradient to be perpendicular to it?
I missed the first part of the question. So if
you're working in two variables and
yeah.
The gradient is perpendicular to the level curve, and if you're in three variables to the level surface.
Yes.
But then after a certain point,
well, so in higher dimensions, the principle still holds. You just can't visualize it.
Okay.
So like, for example, if I wrote down a function of 4 variables, the domain is 4-dimensional space, which who knows what that looks like. A level thing in 4-dimensional space would be a level 3-dimensional blob, which is impossible to visualize. But whatever that looks like, the gradient vector will be perpendicular to it. So it just gets harder to visualize. Nice. Hopefully the test went well, Hia. Glad to see you again. All right, so we want this vector to be parallel to this vector. That is to say, we want the vector 2x plus z, z x plus y, to be parallel to, which is to say, should be some scalar multiple of the vector 4, 2, 3. Okay. Then as usual, this, once we match up components, this just turns into an algebraic system of equations. I'll get 2x plus z equals 4 lambda, z equals 2 lambda, and x plus y equals 3 lambda. That'll be the system of equations that we have to solve. So the role of the lambda here, the scalar multiple, this is coming into play because this vector, I don't really have a control on how long it is. So as I track this gradient, so here's my surface, and as I track the gradient vector going around the surface, it's got a mind of its own, so it just has a certain length that I can't really do anything about. And because I can't do anything about that length, but I want it to be parallel to this fixed vector, I can't say that they're going to be the same. Like, I don't know that that would ever happen. because it might get to the point where they're parallel, but that the gradient vector is like 40 times longer or something. And that's just something that I can't control. So the idea is that I want them to be parallel, but I can't quite account for their lengths exactly. So we just need to check for when this vector is some scalar multiple that I don't know what that is times the other one. Right, and so the idea, like the point where the reason we're doing that is because I want the planes to be parallel, exactly. And to check for when the planes are parallel, I want their normal vectors to be parallel, and that's just what it means. Okay, so here we are. We have an algebraic system of equations that I want to solve. Kind of like on the midterm, in general, this could be a little tricky. It might be very straightforward. Usually a good general strategy for these kind of things is to solve for x, y, and z in terms of the scalar, and then plug that back into the original equation for the surface. That's a good general strategy. Let me write that down. General strategy. Solve for x, y, z in terms of lambda. Then plug into surface equation. That's what I'll do. Why is it wrong to just plug in the normal vector from the parallel plane? Well, so the first question, I don't know if I quite understand, but it would be incorrect to say, I just want this vector to be literally equal to the other vector. I don't know that that ever happens. That's the reason why we need this lambda. Like I said, this gradient vector, as you track it around on every point of your surface, it's got a mind of its own. It has a length of its own, and you can't do anything about that. So like, let's say the planes are parallel here. Maybe the gradient vector is like this long. Is that necessarily going to be equal to the normal vector here? No, it might be some scalar multiple. And we need to account for that possibility. So that's the only role of the lambda, is that we're accounting for the fact that the normal vectors that we write down might not be the same. They might just be multiples of each other. Do we want to make them an equivalent length? I don't know if I understand that question, Eric. Really, I wouldn't think super hard about this kind of stuff. All this is just the definition of what it means for two vectors to be parallel. That's it. If I asked you A and B are parallel, what does that mean? You would tell me that A is some scalar multiple times B. That's it. So I'll let you ponder that. Okay, anyway, we need to do some algebra. And like I said, I want to solve for x, y, and z in terms of lambda. How would I do that here? Well, z is already in terms of lambda, so that's good to go. Now I could get x in terms of lambda by plugging this in here and solving for x. And then once I have x in terms of lambda, I could use this third equation to get y in terms of lambda. Nice. Okay. So let me do that, and we will be on our way. So z is 2 lambda already. That was easy. And then using the first equation, this tells me that 2x plus z is 4 lambda. So subtract 2 lambda and then divide by 2, and it looks like x is using the third equation. This tells me that lambda plus y is 3 lambda, which means y is 2 lambda. Okay, and so I've got x in terms of lambda, y in terms of lambda, and z in terms of lambda, which is exactly what I wanted. Then the next part of my general strategy was to plug these expressions into the original surface equation and then solve for lambda. So plug this into, I've erased the original surface equation, but it was x squared plus x z plus xy, maybe, equals 14. Oh, thanks. YZ. All right, so I'll plug in all these orange boxes. This would tell me that x squared is lambda squared plus x times z is 2 lambda squared That has to equal 14. And now I've got an equation only involving lambda that I can solve. We'll solve for lambda, and then we've got x, y, and z in terms of lambda, so that will spit out the points that we actually care about. Because again, the thing to remember about these problems is I don't actually care about lambda. Lambdas doesn't matter, sorry. Lambda is just a tool to get us to x, y, z. The end goal in these problems is the spatial point x, y, z. Anyway, let's see, what do we have? 3 lambda squared plus 4 lambda squared is 7 lambda squared equals 14. So therefore, lambda squared is 2. And so lambda could be plus or minus the square root of 2. Nice. Okay, so I've got 2 lambda values, which is going to give me 2 different points, and that'll do it. So lambda, when lambda is the positive square root of 2, what point do I get? X is lambda, y is 2 lambda, and z is also 2 lambda. That's 1 point. And then when lambda is negative root 2, I get the point negative this. Negative root 2, negative 2 root 2, and negative 2 root 2. So those are the evidently 2 points on this surface where the tangent plane is parallel to this given plane. And we're done. Cool. All right. Making good time. Yeah, that's a good explanation too. All right, let's do this. This will be a throwback to week 2. Here's what I want to do. I want to find the projection of a vector. Find the projection of, and the vector I picked was 1, 2, 3. How creative of me. And what am I projecting to? I'm going to project onto the intersection of 2 planes. So find the projection of this vector onto the intersection of x plus y plus z equals 1. Oh, hold on. I'll just make the null 0. X plus y plus z equals 0, and 2x minus y minus z equals 0. Okay. So what's the deal here? There's a couple things going on. The first of which is we have two planes that are being intersected. So for the review session tomorrow, I'm going to do completely different examples. So like tonight, I'm going to try to cover a wide swath of all the material from the quarter, and I'll do the same tomorrow evening, but I'll do different examples for the sake of variety. Okay. Oh, right. So one of the things that we have happening is that we have two planes that are being in a line. And what we want to do is I've got some other vector, and I want to project that vector onto that line of intersection. That's the picture. Okay, so then I think about, I ultimately need to project some vector. How do I project vectors? I only know how to project a vector onto another vector. That's the only thing I know how to do. So somehow I need to rephrase this mess as project this vector onto this vector. So then I'm thinking, okay, well, I've got these two planes. What vector do I want to, they're kind of floppy planes, but I have these two planes. What vector do I want to project onto? Probably a direction vector for that line of intersection. So what I'm trying to do now is find a direction, or find a vector parallel to that line of intersection. That's what I'll project onto. Okay. So this is a lot of words. Sorry. How do I find a vector directing the line of intersection of two planes? Take the normal vector here, the normal vector here, and cross them. So that's the fact to remember, is that the intersection of two planes is going to be directed by the cross product of their normal vector. Okay, that was a lot. I'm going to write that down. For the previous question, oh, so why couldn't we plug in lambda times 423 to get the points? Because the vector 423 doesn't represent a spatial point. It represents the normal vector of some plane chilling over here. So the vector 423 is like over here. It's the normal vector for some plane. The points that we're trying to find are points on the surface. They're x, y, z points satisfying this equation. That's why. Okay, let me write down some of the whatever I just said. So I guess if I were writing a solution, I would say solution. Then I would say the line of intersection of the two planes has direction vector given by the cross products of the normal vectors here. So this would be the vector 1, 1, 1 cross 2, negative 1, negative 1. And so now we just have to compute a cross product. As usual, I don't care how you compute the cross product as long as you do it correctly. So how do I do this? Let me just do it in really quickly. And like I said, you can do whatever you want. You can do the whole IJK thing if you want. The cross product is going to be the vector negative 1 minus negative 1 is 0. And then 2 minus negative 1 is 3. And then negative 1 minus 2 is negative 3. So there's a probably 95% chance I did that correctly. That's the cross product. This is the vector that I want to project onto. So the projection we care about is okay, let me do this. Let me call this vector B. Let me call this vector A, just so I can write this a little more compactly. The thing that we now want is the projection of A onto B. So is the projection of A onto B. And now we just have to remember or look up in the book or whatever how to compute a projection. If you forgot, it's A dot B over B dot B times B. So we just have to compute this now. All right, so maybe I'll just do this in one fell swoop. A dot B on top is going to be 0 plus 6 minus 9. In the denominator, B dot B is going to be 9 plus 9. And then B is the vector 0, 3, negative 3. So this is negative 3 over 18, which is probably negative 1/6. Is that right? Something like that. Okay, that would do it. So, point of this problem, you should know how to project a vector onto another vector, and you should also know how to think about, say, the intersection of two planes, and maybe how to find a line directing that. One sec. Given two planes, is it possible to obtain the curve that describes the set of points or the line of intersection? I could say, for example, parameterize the line of intersection. To do that, you would just need a direction vector like we got here, and then you would need to find at least one point on the intersection. Once you have that, then you could write down the entire line. Question? Oh, so how would you find a point on the intersection here? You just have to find something which solves these equations simultaneously. And for two things like this, you could just like guess. For example, what if 0, 0, 0? That works. Okay. Now, if it wasn't that simple, you could say something like pretend x and y are both 0, and then figure out what z has to be, or something like that. Yeah. John.
How would this problem have been different if the two vectors given were equal?
It wouldn't have changed. The reason why I hesitated at the beginning, because I was worried about just the meaning of the question. Like, so these planes actually contain the origin. And I was just worried about like how you would interpret if they didn't contain the origin. Like if it was over here, what would it mean to project this vector onto this line? That's not so well defined for me. So I don't think that would happen in a problem like this. Maybe the thing to point out is that this doesn't change, right? Like if the planes were over here, you could get a vector directing that line of intersection in exactly the same way. Nice. Should the formula be multiplied by b or the unit vector of b? So it depends on how you write the formula. The way I wrote it is fine. Another way that you could write this is a dot b over the norm of b times the unit vector in the b direction. And these are the same thing. So you can write the projection formula however you want. Nice. Okay. Another one down. Oh, let's actually do something a little similar to what Abhishek just asked about, which is I want to parameterize the intersection of two surfaces next. So in this specific case, I would want the answer to be a vector. So just based on the way I phrased the question, I said find the projection. When we talk about projections, like the projection of a vector is a vector. So I would actually want, in this case, the vector. If the question said like find the component of something, then you could just give the component. Okay, next up, parameterize the intersection intersection, is how you spell that, of the two surfaces. Let me say nothing too crazy. Let's just do x squared plus y squared equals 4. And then 2x minus y minus 3 or plus 3z equals 10. So what's happening here? For fun, we can think about the geometry, or you can watch me fail at drawing a picture, but we don't really need to do that here. Just, it's never a bad idea to think of pictures or draw pictures if you can. But what does this surface look like? Well, x squared plus y squared equals 4. In the xy plane traces out a circle. But this is a surface. There's no restriction on z, so that circle just goes up and down forever and ever and ever, which means this is a cylinder of radius 2. This thing here is a plane. So I've got a cylinder, and we're chopping through with a plane. Okay, so let me draw a picture for fun. There's my cylinder. This is the hard part. Oh, yikes. That's a plane which is shaped like that for some reason. And when they intersect, I get some kind of something like that. If that makes any sense. That's the thing that we need to parameterize. Okay, like I said, we don't actually need to draw a picture to do this, or we don't need to think about the picture to do this. I think it just helps. Typically, the way I think about these kind of parameterization problems where I want to parameterize the intersection of two surfaces, a good way to approach that is to look at one of your equations and see if that equation will dictate what, say, x and y have to be. And then once you've chosen x and y, you can use the other equation to tell you what z has to be. It doesn't always work like this, but that's a good general strategy. In particular, what I latch on to is I look at this equation and I think, oh, I can definitely find two functions for x and y which satisfy this, because like I said, in the xy plane, this is just a circle. So in other words, I can use this equation to tell me what x and y are. And then once I've picked x and y, using this equation, I won't have a choice, and z will be chosen for me. So let me write that down. So I would say, so I don't think there's a whole lot of work to show for a problem like this, as long as you know what's going on. I would just say a parameterization of the intersection. Holy cow. Intersection, I don't know why that word's giving me so much trouble, is x and y. And these two functions definitely satisfy this first equation. But then I have to figure out what to call z. But on the intersection, x, y, and z have to satisfy this equation, so I don't have a choice. If x is 2 cosine t and y is 2 sine t, solve for z in this equation, and that's what z has to be. I don't have a choice. So let me do that in one go, and then if something I did is confusing, let me know.
So you're just plugging x and y?
Yep, so all I'm going to do is just plug in these two expressions for x and y into this equation and solve for z. And that would do it. So if I attempt to do that in one go, this would be like 1/3 times 10 minus 2x would be 4 cosine t. Plus y would be plus 2 sine t. There you go. These would be parametric equations which describe the intersection of these two surfaces. Done.
Can you explain how you got x and y?
Yeah, so one way to think about it is the equation x squared plus y squared equals 4 is x squared plus y squared equals 2 squared. From experience or geometry or whatever, I know that this describes a circle of radius 2, and I've parameterized probably 2,000 circles in my life, and I know that I could do that with cosine sine with a factor out here to adjust for the radius. But then a good thing to do is, like, I think this is the most insightful thing to do. Let's just check. Like, let's just make sure that these two equations actually satisfy this. X squared would be 4 cosine squared plus y squared would be 4 sine squared. And then if I factor out a 4, I get cosine squared plus sine squared. And that is 4. So checks out. Check.
What if we don't get so lucky that it's a nice circle?
So the scenario when you get two equations and both equations have all 3 variables, you'll just have to do an algebraic operation to eliminate one of those variables. Yeah, like subtract them or something like that. But ultimately, you want to do something to eliminate one of the variables so that you do get an equation with just two. And then you can do this. So that's really the only other complication that could arise. We could do something like that at some point if you want. How to parameterize. How to parameterize what? Okay.
So the final answer, would you write those as a vector?
If you wanted to. I would be fine with this, but if you wanted to, you could also write this as R of t is the vector with three components.
Oh, where do you
Be
get
fine.
the 3 components?
X, Y,
Oh,
Z.
okay.
Yep, so like this would be the first component, second component, third component. Cool. Okay, I need a gummy break. Last couple nights ago, we did Q&A while I was eating, so you can ask me anything while I eat my gummies covered in chalk.
What questions do
Could you
ask?
throw me another one to try?
This one that is about it.
Oh, yeah, it was. It was just a bad catch.
What questions did you have last time?
Favorite number? I don't know if I thought of that. I feel like 4 is a pretty good number. Tattoo is my heart rate. Oh, someone asked about my favorite mathematician the other night, and I wasn't sure. Let me think. Tattoo's my heart rate. This corresponds to one day, and this corresponds to another day. This was a really bad day. This was a really good day. Let's put it that like that. Favorite mathematician?
Is the bad heart rate higher?
Not really. They're pretty similar.
When did you get it?
Last summer. Yeah, they're so good.
And it looked healthy too.
No, like probably not, but let's look at it.
I don't know if this is my favorite it's not my favorite mathematician, but if you guys don't know who Gregory Perelman is, you should look him up. He's pretty interesting.
Is he right now or is he dead?
Well, he kind of quit doing math.
What is he doing?
He solved the millennium problem. I don't know if you've heard of millennium problems. There's like 7 major unsolved problems, and they're the hardest problems ever in the history of math. And only one of them has been solved. It was by this guy. And if you solve any one of these problems, you pretty much, it's the guy that solved the Poincare conjecture. He was awarded the Fields Medal, which is like the Nobel Prize in math. He declined it.
Wow.
He was offered $1 million. There's $1 million cash prize if you solve the millennium problem. Declined it, and then he quit math.
What the hell?
It's super
Who gives
weird.
you $1 million? Like, where is the money?
I would take $1 million and then
That's so weird. I wonder what he does now. Like, he doesn't have a job?
It is a pretty like power move to do that.
Maybe if you're that smart, you don't need the money.
So Abhishek, I didn't quite understand what your question was. I think I asked you, you said how to parameterize, and I asked, Alex asked about workout program. Since all the gyms are closed, I went to the park and I did a bunch of pull-ups. So I guess that's going to be the move. All right. Snack break over. Let's see. Oh, let's do a maximization problem. Okay, let's do this. So the function's going to be let f of xy be oh, right. So the idea there was that if you get a scenario where you have when you have all three variables in both equations, what I would do, it kind of depends. It's hard to say in general, but what I would do is I would do some algebraic manipulation, like set them equal to each other somehow, or like subtract something so that you eliminate one of the variables. That will give you an equation with only two variables, and then you can do this kind of thing that we did. Yeah. So that was my quick answer, but roughly do some algebra to eliminate one of the variables to get a scenario where you only have two of them. Okay, so, oh yeah, I was gonna look at the function. X squared plus xy minus y cubed. That's the function we're working with, and I want to find the global min and max on a square. Find the global min and max on, and I'll give us the region this way. I just said it was a square, but the way I'll write that is I'll say x ranges between -1 and 1, and y ranges between -1 and 1. Okay.
Just saying like global extrema, that's the same.
Yeah, if the problem says global extrema or something like that, then they're just looking for both global min and global max. Okay, so as usual, a problem like this is going to be pretty tedious. It's going to take a lot of work, but let me outline the general strategy first, which is just like in the one variable case. Let me draw the same picture I always draw in case any of you haven't seen me draw this yet. In the one variable case, if you're given a continuous function on a closed interval, and you want to find the global min and max, what do? You look for critical points on the inside, which would be like here and here. Because, for example, here the maximum occurs, but is it enough to check critical points? No. You also have to check the endpoints. It's the same deal in higher dimensions. The most difficult complication is just checking the boundary becomes a lot more involved. How do you find critical points of a multivariable function? You look for where the gradient is the zero vector. All right, so the gradient in this case, the x derivative is 2x plus y. And the y derivative is x minus 3y squared. Okay. So critical points here are going to occur when both of these are 0. So the system of equations that we want to solve is 2x plus y equals 0 and x minus 3y squared is 0. Okay, so we've got more algebra to do. Video skipping. Oh no. All right. So what would I do? I would probably use the second equation to say, well, x has to be 3y squared. And then if I pop that into the first equation, this tells me that 2 times x, so 2 times x is 6y squared. This should, plus y. This should be 0. And then I can use this equation to figure out what y has to be. In particular, I would probably factor out a y, and I would get y times 6y plus 1 equals 0. This gives me two y values. Either y could be 0 or, I'm probably going to regret this later, y could be negative 1/6. Using those two y values, we can get x values. X was, x was 3y squared. So when y is 0, x is 0. That's not too bad. So I get the point 0, 0. Okay, and then when y is negative 1/6, we get 3 over 36, which is 1/12. So that gives me the point negative 1/6, 1/12. Yes, thanks. Good catch. 1/12, negative 1/6. Okay. Next question you always have to ask when you get critical points is, do I actually care about those critical points? In other words, are they in our domain? Unfortunately, they are, because the domain is any point x and y where both coordinates are between negative 1 and 1. Both of these points check out. Okay, so maybe over here, I'll start compiling our list of points to check. Which, just a word of warning, once we generate all the points, I might be too lazy to plug all of them into the function. So I might skip that part, even though I probably shouldn't do that. That would be a bad TA move. But I might do that just for the sake of doing other things. Anyway, so far we've generated two such points, 0, 0, and 1/12. All the critical points on the interior of the region. The shitty part is going to be, now we have to check the boundary. Now let me draw a picture of the domain to have up here. The domain is all x values between negative 1 and 1, and all y values between negative 1 and 1. That's a square. That maybe is or isn't a square, but that's what the domain is. And it has corners, for example, 1, 1, 1, negative 1, etc. Negative 1, negative 1, and negative 1, 1. And so far, we've found 2 points that we care about, 0, 0, and then this other ridiculous point, which is like here. Yeah, video skipping might just be something to live with, unfortunately, for the next quarter. I don't know. Unless there's something I can do differently. I don't know if there is, though. Let me know if you're a tech whiz. All right, so now we need to check the boundary. The boundary has 4 different components. So this is going to require 4 different one-variable optimization problems. So we'll tackle them one by one. I don't want to forget what the function is, so I'm going to keep that up here. And because this is so tedious, I'll probably keep what I write on the brief side, which is probably fine in your solutions. So here's the function that we're working with. Let's check the top edge. How do I check any one of these edges? Very generally, when you check the boundary, what you want to do is you want to parameterize the boundary curves. Now, in this case, it's relatively easy to use or to find parameterizations. And for example, the top edge here is given by the equation y equals 1. So one way to think about what we're doing to check the boundary is we're just going to set y to be 1. So the top edge is given by the equation y equals 1. But, this is important, the equation y equals 1 is this. It's the line that goes forever and ever and ever and ever. I don't care about that. I only care about the segment from -1 to 1. So y is restrained to live between -1 and 1. So if the domain was only -1 to 1 for x, that would not be a bounded region. So you could try to find a min and max, but it might not exist. But it might be the case that there would be no minimum or maybe no maximum or neither. Anyway, here's our restriction. I plug this in. I would get f of x comma 1. Oh, sorry, not y does range from -1 to 1. The x values range from -1 to 1. So the boundary function I would care about is f of x comma 1, which would be x squared plus x minus 1. And then I usually give this a new name. I'll call it g of x because it's just a one-variable function. Yeah, probably the only kind of regions you'll get are like a triangle or a square or a circle, or, I mean, not necessarily, but you'd have to be given some data about the curves. So for example, I could give you a region like a region bounded by y equals x squared and y equals x, or something like that. And that could be the region. So that's not strictly like a triangle or a box or something like that, but you have data about how to describe the boundary curves, and you can use those for your parameterizations. But I don't think you'll get anything too crazy. Like it would be like if he was like, oh, like find the maximum on that thing. Like you couldn't probably do that. So it'll be a geometrically simple shape if he gives you something like this. Okay. So what do? We find the min and max, or we find all possibilities of this on this interval. How do you do that? You look for critical points, and then you check the endpoints. So g prime of x is 2x plus 1, which means we have a critical point when x is -1/2. This generates the point -1/2, 1. And that's a point that I care about. So I'll add that to the list over here. I'll draw it on the picture. -1/2, 1 is like right there. That's the only critical point on the top edge, but then, like I mentioned, we've got endpoints to check. So the endpoints when x is -1 and 1 give us the point -1, 1, and 1, 1. And that corresponds, oh damn, that corresponds to these corners. So the upshot is that in a problem like this, you're going to have to check all the corners, unfortunately. So let me record those. -1, 1, and 1, 1. And I might run out of space on my list of points. Yeah. Okay. That's the top edge. 1 down, 3 to go. So I'll fly through the others because they're going to be pretty much the same thing. Like I said, unfortunately, there's a lot of repetition involved here. If I do the bottom edge, it's very similar, but it's going to be given by the equation y equals -1. X values are restrained from -1 to 1. The boundary function that I would get would be f of x comma -1, which is going to be x squared minus x plus 1. Critical points of this thing are going to occur when the derivative 2x minus 1 is 0. So I have a critical point when x equals 1/2, which generates the point 1/2 -1. Add that to the list. Draw it on the picture. 1/2 -1 is here. And then we're also going to have to record the endpoints. I'll annoyingly squeeze that down in here. Endpoints give us the other corners, -1, -1, and 1, -1. So I'll add those to the list. And another edge down. Yeah, I don't like these either. This is not, I love math, but this is not the kind of math I love. Anyway, we've accounted for all the corners, so I don't have to worry about those. Now we just have to do the right and left edges, and then we'll be done. And like I said, I'm going to be way too lazy to actually plug in all these points. I don't think you would get anything this insane. I just wanted to do this process so you can see like all the different things that can happen. And in theory, you would have to check all of these points, as annoying as that is. So let me do the left edge. This is given by the equation x equals -1. The boundary function is now going to be in terms of y. The y values are restricted from -1 to 1. And this boundary function would be 1 minus y minus y cubed. Uh-oh. G prime of y is -1 minus 3y squared. Is this ever 0? Nope, never 0, so no critical points. And I've already accounted for the boundary of the boundary. Already accounted for endpoints.
Can you explain
Yeah, sure. So y squared is always positive. So -1 minus a positive number is always going to be negative. Or set it equal to 0 and try to solve it, and you'll see what happens. Okay. And the corners I already have on the list. Oh, yeah, sorry. Thanks for yelling at me. Okay, so I've already accounted for the endpoints, so that was the left edge. Let's do the right edge, cross our fingers, hope we don't get any more points. The right edge is given by the equation x equals 1. Again, y is restrained from -1 to 1. The g function here is going to be f of 1, comma y. Oh, which is 1 plus y, damn it, minus y cubed. Unfortunately, I think this will have critical points because g prime of y is 1 minus 3y squared. And so we're going to get critical points when y is plus or minus the square root of 1/3. Okay, so that gives us 2 points. 1, comma, 1 over root 3, and 1, comma, -1 over root 3. So on the right edge, these are the points like here and here. Add those to the list. We've already accounted for the endpoints. And like I said, this is extreme. Oh, no, you can yell at me through chat, I guess. You could also yell at me in person the next time you see me, but don't feel bad about yelling at me. Okay, like I said, this is insane. You probably won't get something like this, but this is a good problem to demonstrate like how this process works and how you would generate the list of points to check. So like I said, I really don't want to do this, but what would you have to do from here? You'd have to plug in all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these points into the original function. Whichever one spits out the biggest number, that's the global max. Whichever one spits out the smallest number, that's the global min, and that would do it. Like I said, I really don't want to do that, so I'll just say, if it's fine with you guys, unless you really want to see me struggle with.
On the test,
Yeah.
should we show our work to do that and then use calculator?
Yeah, it's a good question. Honestly, so if I were taking the test and this question came up, here's legitimately what I would do. I would get here and I would stop and I would move on and I would do all the other problems. And then after doing all of that, I would see how I feel. And if I was sick of taking the test, I would just call it quits and turn it in and maybe take a -2 or something for not plugging in all the points. Might not be worth your trouble.
We have 24 hours.
Yeah.
So if you have literally nothing better to do but Math 32A over the 24 hours, then I don't think there's any work required. You could just say like f of this is this, f of this is this, f of this is this. Just plug them all into your calculator, and I don't think you have to justify that anymore. I would probably just stop here and then. And so, one reason for that is because I know how I grade. And so I can't speak for the other TAs. And as we've seen, different TAs grade quite differently. But if I were grading, this would be like 9 out of 10 getting here. And I know that you can punch numbers into your calculator. And I think if you just said what I would say, which is like plug all these points in into F, and whichever one returns the largest / smallest value respectively is the max, min, respectively. Okay. That's what I would do on the test, and then I would give that a 9 out of 10. And I'll take that. So, but if you wanted to plug them in, you just plug them in the calculator, and I don't think you need to justify anything beyond that. Whew, okay, so that was a lot. And we're kind of done with that one, at least. Takeaway and summary. Look for critical points on the inside, then check the boundary. And very importantly, when you check the boundary, if the boundary has boundary, which just means if there are corners, you have to check the corners as well, unfortunately. Yeah. So yeah, so when you, even if it was a circle, when you write down your boundary function, you will have endpoints for your parameter. It doesn't correspond to necessarily like corners or anything like that, but every time you write down a boundary function, it's going to have a closed parameter domain. And it may not seem like it geometrically, but it will still be. You will always have endpoints to check.
But doesn't a circle, if it's a closed circle, isn't the endpoint like isn't the endpoint necessarily a critical point? Like
no.
The endpoint was the max or min.
Nope.
No, it's a circle. Unless it's a helix.
But when you, so how do you describe a circle? Cosine t sine t.
Yeah.
But what's your domain for t?
0 to 2.
All right, 0 to 2 pi. Oops. I don't want to break here.
Oh,
Nice job. Yeah.
Is it as good as
Oh, it's fantastic. Yeah. Yeah, sorry for my poor handwriting. If that's what you guys are. Let's see. Okay, I need to scroll back a bit. Are all the points either global or local maxes or mins, or could they be saddle points? Yeah, critical points could be saddle points. That could definitely happen. Yeah, we can do a circle. I'll do a circle problem tomorrow, maybe. Or later tonight if I'm still going strong. Okay, let's move on. Oh, what's the question? She was asking about the circle scenario. I'll talk about the circle scenario some other time, or if any of you were in discussion from 2 weeks ago and took notes, I did a circle problem. A little quickly, but I did one. Did I tell my roommate not to stay up? Yes. So, because we share a shower. And the shower's through his room, but we usually go to bed at like 10. So he'll be asleep by the time I get home, and so I'll have to shower some other time. That's the end. It's a long story. Okay. What are we doing? Oh yeah, we're moving on. I want to switch it up a little bit. Okay, let's do something easy after doing that. But something that you should remember how to do. I want to find the area of a triangle. That won't be so bad. Oh, right, and if anyone was trying to figure out whatever I wrote here, plug all these points into F. Whichever returns the largest / smallest value is the max / min, and then this says respectively. Okay, so next up is find the area of the triangle, and I'll give us the corners. With corners 1, 1, 2, 2, 0, 1, and 3, -1, 1. How about that? Okay. We'll get this disaster out of here. So what's the deal? Again, this is a throwback type problem. The deal is that we're going to use the cross product to figure this out. The picture is that we have 3 points, which I'll draw like that. I care about the area of this triangle. The game plan is to use the cross product, and in particular, I could construct 2 vectors which generate the edges, 2 of the edges. And then I think about what does the cross product of those 2 vectors tell me? The cross product is a vector, but if you look at the length of that cross product, I didn't draw that very well. The length of the cross product of, say, A and B gives you the area of that parallelogram. So the magnitude of A cross B is the area of the parallelogram. Well, so then to get the triangle, it doesn't really look like it based off of my picture, but the triangle is half of the parallelogram. So I just take this and divide it by 2, and that'll do it. Okay, so first I need these vectors A and B, and I can get that by just picking one of these points as an anchor here, like 1, 1, 2. And I can get A and B by subtracting. So for example, I would say let A 1, 1, 2. And then I'd let B be the vector, the other point, 3, -1, 1, -1, 1, 2. And those will be my 2 edges. So let's see, this is the vector 1, -1, -1. And this is the vector 2, -2, -1. I forget what I just said. 2, -2, -1. Okay.
When you set it up, the vector 2, 0, 1 would be like on the top,
That's correct. Yeah. So maybe if let me do that. So this, as I've computed it, would be 2, 0, 1, and then down here it would be 3, negative 1, 1. And one thing to point out is that you don't have to do exactly this. You could pick any of the points. You could find any of the edges. It doesn't matter. Any of the 3 edges will give you the correct thing. All right, so let's cross them, take the length, and move on. So the area of the triangle that we want is going to be 1/2 of the magnitude of the cross product. Oh God, so now I have to compute a cross product again. So this will be 1, negative 1, negative 1, cross 2, negative 2, negative 1. Which will be 1 minus 2 is negative 1. Negative 2 minus negative 1 is negative 1. And negative 2 minus negative 2 is 0. I may have done that correctly. The magnitude of this vector is the square root of 1 plus 1. So I get root 2 over 2. That was pretty nice. That would be the area of that triangle. Do both vectors have to? Nope. So you could take, not only could you pick different sides, but you could take like this vector and then this vector. That would also work. That would give you the same area. You could think about maybe why that's the case geometrically if you want. Yeah, so Abhishek's saying, you know, they actually do kind of start at the same point, but what you'd have to maybe think about is the area of this triangle the same? And it will be. Because the area of this parallelogram, that's the same parallelogram as that parallelogram. So that would work. Nice. Sweet. Man, we are flying through these examples. Okay, let's find and classify some critical points. We haven't done that yet. This will be the second derivative stuff. Okay, so next up is going to be, here's our function. Let f of xy be x squared y minus xy squared minus 3x. Multivariable function. I want to find and classify all critical points. Find and classify all critical points. I have not done implicit differentiation yet, but I did make a video all about implicit differentiation on the YouTube channel. So I'll defer to that for now, and then if you still feel uneasy about it or whatever, you can let me know. Maybe tomorrow we can cover that. But I think the video is called Multivariable Implicit Differentiation, something like that. Oh, chain rule, we should do that. I didn't think about that. Chain rule, okay. Oh, okay, so we need to, yeah, like I said, trying to make it big on YouTube, though. All the clicks I can get, I'll take them. How do we find critical points? We've done this already. We're going to find where the gradient is 0. So we've done something like this. We'll do it again. The difference here is that I want to classify them. So this is where that whole second derivative stuff is going to come into play. Yep, so to find them, we'll do exactly what we did before. And we'll say critical points occur when the gradient of f is the 0 vector. So that is to say, the gradient of f here, the x derivative is 2xy minus y squared minus 3. Did I do that right? I think so. And then the y derivative is x squared minus 2xy. Okay. So as before, this is going to generate a system of equations. The system of equations will be this equals 0 and this equals 0. So I get 2xy minus y squared minus 3 equals 0, and then x squared minus 2xy equals 0. Okay, that's what we have to figure out how to solve. What would I do? The second equation looks a little simpler. So if it were me, I would probably latch on to the second equation, and I could say factor out a common term of x. Professor Leonard shout out in the comments. Yeah, I'm going to be the next Professor Leonard. Okay. Or if you check my channel description, my goal is to be the Bon Appetit of the math YouTube world. Don't worry about it. Okay. What was I talking about? Oh yeah, so this second equation, factor out an x here, and I get x minus 2y equals 0. Two cases that we have to account for. X could be 0, or this could be 0. So the one kind of thing that you have to be careful about when these systems of equations get a little complicated is, for example, it might be tempting to start with this equation and say like, oh, I'll just divide through by x or something like that. You can do that as long as x is not 0. And that's a scenario that you have to account for.
I started off by each equation had a 2xy.
Oh yeah, that could work
But
too.
that, it
Oh,
like,
did
didn't
that-
run nicely, I don't know.
Yeah. So they both have a 2xy. You'd get something like x squared minus y squared minus 3 is 0. Yeah,
It's like,
that's not wrong, but may not be super helpful. Yeah. I wish I could animate like 3 blue, 1 brown. Joe likes cooking. I do. Yes, I will be making videos for 32B. So in case you didn't know yet, I will be a 32B TA next quarter. I am planning on streaming all of my discussion sections and then uploading them here afterwards. And then I'll probably make regular videos about 32B topics as well. So if you're taking 32B, you can, even if you're not in my section or not in my lecture, you can find anything I have to say right here. Okay, I need to catch up with all these comments. Sally would die for Claire. Me too. I don't know about 33A. We'll see. I don't know what my teaching is going to look like next year. So like I said, even if you're not in my 32B discussion, the one good thing about all this online stuff next quarter is that literally anyone can watch. So stay tuned. Noah White. Yeah. Okay, let me go back to the math. We've got two scenarios here. If x is, and so what I'm going to do is I'm going to take each of these scenarios and plug them back into the first equation and see if that can tell me something about y. So if x is 0, what does this first equation turn into? It turns into negative y squared minus 3 equals 0. Right? Yes.